Right, so we are on 323. Finished yesterday with On Your Own, 9.1 through 9.3. I encourage you to do those. Spend your time yesterday doing those or finishing them. So if there are any questions on 9.1 through 9.3 you'd like to go over before we kick off into recognizing acids and bases from their chemical formulas. We've already done some of this. Like I said, there's a lot of overlap. There's some things that we've already done that they're going to teach you as if it's brand new stuff in this section. But, or I might have referred to it, I've been through this material so many times, I might refer to things and then realize, oh, I spoke about it a little bit or used it maybe even just before we taught it. That's not intentional to confuse, it's just me being distracted and not recognizing what I have and haven't presented to you yet. I presented other classes. So. All right. They note in the text that the acids that they've presented to you so far, that every one of them has started with what atom in its chemical name? Virtually every acid up to this point. Correct. Every acid up to this point, and they use HF as an example. And they say every acid that they presented to you up to this point, with the exception of one, the acid has, in its chemical formula, has started with a hydrogen. So HF, HCl, H2SO4, all those acids, every one of them so far has started its chemical formula with a hydrogen, the exception being C2H4O2. Now this is an acid, it acts as an acid, but it's the only one we've seen so far that doesn't start with a hydrogen. So what they're basically telling you in this section is, as you look at your balanced reaction equation, and you're looking, and you're told that it's an acid-base reaction, first thing you should do probably to identify the acid is see which of those reactants begins with a hydrogen. That'll start you on your path. The other common thing is that not only do the acids begin with a hydrogen, but all but one of the bases that we've seen so far has a hydroxide ion in it. And I know I mentioned that yesterday, that hydroxide is going to be the most common base that you see. And so, as you're looking at the reaction equation, looking at the reactant side, you're looking for hydrogens, which are going to lead you to the acids, and you're going to look for hydroxides, which will lead you to the bases on the reactant side of the equation. Now, the only exception they had thus far to the hydroxide is ammonia. That's been the exception so far. Ammonia acts as a base, but it doesn't have a hydroxide ion in it. This is a covalent molecule, but it still acts and functions as a base. One other thing too that I want to mention, we did talk about sulfuric acid, H2SO4, a little bit in here. One thing that I want you to recognize is that even though you might see in this a polyatomic ion, that's not actually the way this molecule is put together. I mean, look at all of this, right? This is, are there any metals in here? Yeah. No, these are all nonmetals. Given that they're all nonmetals, what kind of bonds are present in this molecule? It's all covalent. When you look at this, you see the SO4. Remember, we talked about polyatomic ions and how that they are covalent molecules. So a sulfur and 4 oxygens come together to form a polyatomic ion. And so if we see an SO4 like that, we would say, well, I've got my polyatomic ion here. We're used to seeing polyatomic ions that then have a metal that they attach to, right? So if we had a metal, a sodium, or potassium, or rubidium, or beryllium, one of these metals, we gave you a molecule that had a metal and this polyatomic ion, you would say, well, it's formed an ionic bond. Remember, the polyatomic ions are covalent molecules which act as ions and form ionic bonds with metals. That's the definition of them. But in this case, it's not bonded with a metal, but it's bonded with a nonmetal. And so these are covalent bonds bonding to the covalent polyatomic ion. It's not truly a polyatomic ion in that sense. Everything in here is a covalent bond. So you see H2SO4, you may have thought, well, here's the SO4, so I have a covalent submolecule bonded to ionically to whatever's over here, but it's not. Since this is a hydrogen, all of these are bonded covalently, so it's not a polyatomic ion or ionic form. This is a pure covalent form. So don't let that lead you astray as well. That's part of yesterday when you're looking at this saying, well, how would this combine with this? What is the charges? And you're computing what they would be. It's not bonded together ionically. The hydrogens are bonded with the sulfur and the oxygens. Think of it as a pure covalent molecule, not as a polyatomic and a something else bonded to it ionically. It's not that way. Anyhow. Now the acids and bases, remember we talked about common names like sodium chloride, we call it salt. We kind of call that salt, or table salt more specifically. Potassium chloride, H2O, dihydro oxide, we call it water, the common name. Well, in the naming paradigms, acids have their own naming paradigm. They don't necessarily follow, though acids are covalent molecules, they don't follow the covalent naming paradigms. If you want to go ahead and flip over to the next page, table 9.1 on 324 gives you a table that you're not required to memorize, okay? They say in the text, if we ever give you an acid to use, we will give you the formula for it. So hydrochloric acid, we would either give you HCl or just put HCl in the formula and let you hopefully know it's hydrochloric acid, but the fact that it's hydrochloric acid isn't fundamental to the problem. So if we give you an acid, we'll give you the formula for that acid. But frankly, you're going to see these acids so many times that you're going to learn them over time. The acids don't follow the covalent naming paradigm. They have their own common names that we use. You see hydrochloric, hydrobromic, hydrofluoric, and nitric on the first column. The second column, sulfuric, phosphoric, carbonic, and acetic. So acetic acid, phosphoric acid, and so on. Now the bases do follow the naming paradigm. They may have a common name, but in general, they're going to continue to follow the naming paradigm for whatever type of molecule that they are. And there's some common names for these things as well that, for example, in the paragraph below the table, they refer to muriatic acid. If you were to go to a hardware store and get some cleaning agent to clean stains and oxidation and other things off, you'd probably go and buy muriatic acid. Muriatic acid is a form of diluted hydrochloric acid. There's no unique chemical formula for muriatic. It is a certain concentration. I think they list 30-70. Yeah, it's 30% hydrochloric acid and 70% water. So its common name is muriatic acid, but its chemical formula is HCl at that dilution. And again, as in the text, what I'm doing is summarizing the key points of the text. Still encourage you to read the text, but the things that you need to know from the text. That's what I'm covering here in class. All right. Predicting reactions that occur between acids and bases. We're in the middle of 324. Another term for you to know, we've already come up with one term that is not common usage. That's the term amphoteric or amphoteric. Remember what that means? Making common new terms that might sound similar. We're just going to review them several times to make sure you know the distinction. Amphoteric, sometimes known as amphoprotic, means what?
It can be either acid or base.
Right. The molecule functions as either an acid or a base, depending upon what's needed in that reaction. So it can go on either the acid side or the base side. And the most common amphoprotic substance is what? Water.
Well, yeah,
Water. So you can see how convenient that is. We have taps, we have water fed to us all over the place. We need water to survive. And if you have a base and you put water on it, the water will act as an acid to help neutralize it. And if you've got an acid, you put water on it, it'll act as a base to help neutralize it. So water is extremely valuable and extremely common in these reactions. So you're going to be very familiar with seeing acids as well. There's also this new term at the bottom of 324 of polyprotic. It's a little bit different than amphoprotic or amphoteric. Ampha means it can go and be either. Poly means what? If I say I'm looking at a polygon, what does the first part of poly mean? It doesn't apply for polylog, but it applies for polygon. Many, more than one, multiple, good. So we get into what we know as polyprotic acids. All that means is that whatever the formula is, whatever the molecule is, it has the potential of donating more than one proton. If I looked at, for example, the hydrochloric or the hydrobromic, HCl or HBr, how many hydrogens do those acids have that they could potentially give up in a reaction as an acid?
One.
If hydrochloric and hydrobromic are fully into this reaction thing, the best they can do is give up one hydrogen. They only have one hydrogen to give. There are other acids in here that have more. For example, the sulfuric, H2SO4. How many hydrogens can sulfuric acid potentially play into this game of acid-base reaction? I mean, it has two, right? Hydrochloric, hydrobromic, they have one. The sulfuric has two, and phosphoric and hopefully you're seeing the sulfuric and the phosphoric. Okay, so sulfuric acid potentially has two hydrogens to deal. Phosphoric has potentially three hydrogens to deal. So while these two might be called monoprotic, they only have one. These are polyprotic, they have more than one. And more specifically, there's categories within polyprotics. H2SO4, yes, it's polyprotic, but more specifically, it's also diprotic. The phrase protic, that just means proton, okay? When you hear protic, think proton. Amphoteric, it can take or give protons. Polyprotic, it has more than one proton in play. Diprotic, it's a polyprotic that's dealing two. Triprotic, it's a polyprotic that can deal three. That's the magic behind that. Di, tri, poly. Many, more than one. More specifically, diprotic or triprotic acids. Any questions on that? So you might see, for example, on a quiz, is phosphoric acid, and you'd be given the formula, a monoprotic or polyprotic acid. So that would be poly. More specifically, if they asked, what type of acid is phosphoric acid? And have a list of protics, possibilities. It would be polyprotic, it would also be triprotic. Okay, so if polyprotic was an answer and triprotic was an answer, hopefully another one would be both A and B. Both polyprotic and triprotic. In the middle of the page, you can, on 325, you can see that they give us the reaction HF plus K positive plus OH. Just considering those, this molecule and this polyatomic ion and that. I mentioned before that in these types of reactions, that the most, I'm going to write it in its shorter form here too before I do this discussion. Given what we've just spoken about, as I look at these two reactants, I give you a hint to say that this is an acid-base reaction. Which is my acid? Why is HF my acid? Without giving you the reactants over here, right? Before I would give you the reaction, they're the products of the reaction, and you would tell me which is the acid and the base based upon who gives up the proton and who receives the proton. Who's the donor and who's the acceptor. But now, with some other cues that we have, looking at these two, which one, in your best guesstimation, is the acid? Ray said that HF is the acid. I would agree. What cue? Hydrogen is the leading element. Does anything else have a leading hydrogen? No. Does that mean there might be the exception? There could be. But a strong indication that this is my acid because it's the only reactant that has a hydrogen that's leading. I also have a strong indication that potassium hydroxide is what type of reactant? It's a base. Why is it probably a base? Because every base we've had up to this point has had a hydroxide in it. And I know, in its basic form, I said that when you have acids and bases, what is the most common product? When these things neutralize. And that's the phrase, the reaction. As an acid and a base react, they're going to neutralize. Remember yesterday I used an example. I took an acid and a base, and I put them together, and I said the result of it would be salt water. Why? Because the products of the reaction were H2O and NaCl, sodium chloride and water. The sodium chloride would be in solution, so if I drank it, I'm drinking salt water. I started with an acid and a base, and I end with salt water. Looking up here, if I know that this is my acid, what's going to probably happen? It's going to lose this guy right here, right? So this is going to join with what part of this? Do you see that the hydrogen and the OH are going to form H2O? This is going to be a standard type of reaction, folks. A standard type of reaction. Much like I said, here's your carbon, hydrogen, oxygen fuel chain. It has complete combustion with oxygen. What are the products? Okay. This is going to be that fundamental. I have an acid and a base. More precisely, I have an acid and an ionic base. And the results of the reaction are going to be water and salt. And I put that in parentheses. An acid and a base neutralize. Neutralize means in acid-base reactions, they're reacting. And when they're reacting, the acid part and the base part are canceling each other out to form something else. That's when we think about neutralization. So when I say an acid and a base neutralize, that's basically saying an acid and a base react with each other. The acid and the base react, and they form the hydrogen from the acid and the OH from the base combine to form water. And what's left over? We're going to have a portion of the acid, right? The non-hydrogen portion of the acid and the part of the ionic base that's not used up. Form a salt. And the reason I put that in parentheses, form a salt. In this case, it's KF, right? Why? I've got the F, the fluoride from here, the potassium from here that are left over. Think about what I have. I have a negative ion here. I'm left with just fluoride all by itself. So I have an ion left over from the acid, and I have a potassium ion left over from the base. As a matter of fact, this is my positive ion. I've got a positive ion that's left over from the base. The OH has a -1 charge, so potassium has a +1 charge. Does that make sense? Yes, it does. It's a column 1 element, so it's a +1. I've got a positive ion and fluorine, or fluoride, excuse me, fluorine actually was the element. Fluoride is the ion we're left with. It is a column 7 element, right? 7 makes sense. This would be -1 because when we have a negative and a positive, what are they going to do? They're going to come together, right? They're going to be attracted to one another ionically and form an ionic compound. And so the generic expression of this neutralization, in the same way that a carbon-hydrogen-oxygen chain combusts with oxygen to produce carbon dioxide and water in complete combustion, in an acid-base neutralization where there's an acid and a ionic base, it reacts to form water and an ionic compound, which generically in chemistry is known as a salt. So when I say salt in chemistry, I'm not necessarily talking about sodium chloride. Sodium chloride is a type of salt. As a matter of fact, chemists use this term very broadly, and a salt could be basically any ionic compound. Okay? It's an ionic compound. So what the formula is saying here is, in neutralization, the acid and the base react to produce water and a salt which is made up of the leftovers from whatever wasn't used to form water. Again, potassium and OH. The OH is used for the water. Potassium is in play. Hydrogen and fluoride. Well, fluorine, it becomes a fluoride. Hydrogen is taken out to make water. Fluoride is in play. Fluoride and potassium becomes potassium fluoride. Why is it KF? Remember, we put the metal first. Potassium is a metal. Fluorine is a nonmetal. And so the salt is potassium fluoride. So the general question on an exam or quiz might be, an acid and a hydroxide base react to produce what? Water and a salt. More specifically, if given, this is the acid and this is the base, what does it produce? Just as you would have written on combustion, CO2 plus H2O, you're going to write H2O plus a salt. Now what is the salt? Look back to your formula. Pull out the positive ion from the base and the negative ion from the acid and put them together, generally in this order. Why? The positive is going to be the part that acts like a metal, right? It's going to be potassium fluoride. It's going to be the ion from the hydroxide molecule with the ion from the acid that produces the salt. All right, take a deep breath. Any questions? What's on your head right now? What don't you get? Or if you get it, that's fine. It might just be, I understand it, I just need to see more of it. And we will. But does anybody have just a very basic question about how these things form water and salt? Do you at least see that water and salt is what we're driving towards? Specifically when you have a hydroxide, which is the vast majority of the bases you're going to have, are going to be hydroxide bases. Always say, there's my hydroxide, I'm making water with the acid. So take whatever's not used to make water and form your salt. If that be the case, that's all the content for today. We're on example 9.2. Walk through a few examples in the book then. So example 9.2. Give the balanced chemical equation that represents the reaction between hydrochloric acid I need me a smart board. Between hydrochloric acid and rubidium hydroxide. So RbOH. HCl and RbOH. It's like in Word where I got that shadow thing turned on, you know. Forget to turn it off. We'll keep working with it. HCl and RbOH. What we've just gone over. What is probably the acid? Hydrochloric. We know it's, first of all, it's hydrochloric acid. So it's probably the acid. Second, it has a leading hydrogen. This is probably my acid. I can check that by saying what is probably my base. So are there cues that the other thing is probably the base? Well, yeah, it's got the hydroxide ion in it. It's got an OH. This is probably my base. This is probably my acid. As a matter of fact, as you go on, you'll say, yeah, this is my acid, this is my base. Why? Because I know the name of that, and it's got the hydrogen, and it's got the hydroxide, and I know that this is going to produce what? I know that it's going to produce water and a salt. So I can go ahead and put the reaction arrow and go H2O plus, knowing that I'm going to fill that salt in. Right? And I know that whenever I'm looking at rubidium hydroxide, if I take away, let me go ahead and write what we have on the board right now. Write exactly the same thing. Okay? Exact copy of the same thing, but I know that in order to make H2O, what am I using up from this formula? I'm going to be using up the hydroxide, or excuse me, the hydrogen and the hydroxide, because they were used to make water. What's left? I have my negative ion from my acid, and I have my positive ion from my base. These two things combine to make my salt. When they combine to make the salt, what order are they going to be written in? Well, remember that the positive ion is the metal. It comes, that's why it's leading here. Remember, it's leading here, it's acting as the metal. So my metal goes first in the name. I've got rubidium and chlorine. Written another way, the hydrogen and the OH produce this, the chlorine and the rubidium produce that. Rubidium chloride, RbCl. Does it make sense in its formula? Well, rubidium, it's the metal, it's a column 1 element. We know that ionically it wants to have a +1 charge. Chlorine, column 7, it wants to have a -1 charge. A +1 and a -1. They come together. Is it a neutral molecule? It is. Okay? So this is my ionic formula. So hydrochloric acid and rubidium hydroxide neutralize, acid-base term for react, to produce water and the salt rubidium chloride. And that's the first part of example 9.2. You can go through and let's just check the balance. We checked the formulas right. 1, 2, 3, okay. 2 hydrogens, 1 oxygen, yes. 1 rubidium, yes. 1 chlorine, yes. It's balanced. It's kind of like when we do the combustion. You have to go through, even though you know it's CO2 plus H2O, to look at it to make sure that it's balanced at the end. The second formula here. Okay, sulfuric acid. I'm even willing to use a different color if it'll work. That may not happen though, so. I left my computer bag in my office, so I don't have my own to pull from. Let's try this again. Sulfuric acid. It's H2SO4. Write the chemical equation that describes the reaction between sulfuric acid and sodium hydroxide. Okay. So H2SO4 reacts with sodium hydroxide to produce my acid, sulfuric acid. It's a polyprotic acid. More specifically, it's a diprotic acid. Reacts with water, or excuse me, sodium hydroxide to produce, well, you see right now we've got hydrogen and the OHs, so it's going to produce water and salt. It's going to produce H2O and a salt, which is sodium and the sulfate. But I'm just going to put it in here now, knowing it's not, I know it's not technically correct yet, because if I put in a sodium and sulfate, is that balanced? Or second, is this formula right for sodium sulfate? What is the charge of the sulfate polyatomic ion?
No.
Do you remember? We had that chart memorized? Sulfate has a charge of 2 negative, okay? Sulfate has a charge of 2 negative. What does a sodium ion have a charge of? It's column 1 element, it's a +1, right? So what does sodium sulfate actually look like? What's the correct formula? How would sodium and sulfate combine? You would need 2 sodiums, wouldn't you? I need 2 1 positives to give me a total of 2 positive to balance out the 1 negative from, or the 2 negative from SO4, from sulfate. So my formula, whenever I do this combination of sodiums and sulfates, it's going to have to be a 2 to 1 relationship. 2 sodiums to balance out the charge of 1 sulfate. Okay, now I'll step back and take a look at it. Is it balanced? Well, 1, 2, 3, 1, 2. One, 1, 2. Not balanced. What do you propose? We have, where are we lacking? We've got 2 sodiums over here, right? How many sodiums do we have over here? 1. So how do we get 2? Add a 2 in front of the sodium hydroxide. What will that do? Now my hydrogens, 1, 2, 3, 4. Well, over here I have got 1, 2. How do I get 4? Add a 2. Start again. 1, 2, 3, 4. 1, 2, 3, 4. Hydrogens are balanced. Oxygens, 4 plus 2 is 6. Here, 2 plus 4 is 6. Sodiums, 2 sodiums, 2 sodiums. We've already done oxygen and hydrogen, so we're done. Let me check. H2SO4 plus 2 NaOH reacts to produce Na2SO4 and 2 H2O. That's correct. Let's look at it if we didn't remember that sodium, that you need 2 sodiums for 1 sulfate. If we did this balancing routine and we knew that it was, again, H2SO4 and NaOH reacts to produce H2O and NaSO4. I'm just speculating here. It just struck me that maybe we could figure out that it was Na2 from the balance. Because if I look at this, 2 hydrogens, 3 hydrogens. On this side, I only have 2 hydrogens, right? How would I balance that if I thought that that was the formula? I've got 3 to 2. Well, I could go through and multiply each side by 3, this side by 3, and this side by 2, and then my hydrogens would be balanced. It's probably not going to work out. I thought maybe there was a quick key there, but there's not. So let's back away from that line of thinking. Do you remember that the sulfate is in -2, and you need 2 positive 1s to balance it out? So you would have to know this portion right there. Given that, you would know you need 2 sodiums, which would lead you to this, and then you could balance the equation. Right. I'll dwell on that a little bit more. It's been a year since I taught this. It seemed to me that there was a way that we could catch ourselves and figure out that it was Na2SO4 through the balance. But I'll look at that again. The last example then on 327, HNO3 And aluminum hydroxide, AlOH3. What's the reaction between HNO3 and AlOH3? So aluminum here, we know that this is aluminum what? Aluminum, not hydroxide. I'm looking for what is that, what type of aluminum do we have here?
No.
Aluminum, whatever the aluminum ion, its charge is, it has to balance out 3 hydroxides. So what is the charge of a hydroxide ion? It's -1. Hydroxide, remember, polyatomic ion has a charge of -1. And somehow 3 of those balance out the aluminum. 3 at -1 means it's got a 3 negative charge total from the hydroxides. The aluminum has to balance that out, so the aluminum must have a 3 positive charge, which means that this is aluminum 3 hydroxide. Okay? Aluminum, remember, Roman numeral 3. So aluminum, parentheses, Roman numeral 3, and parentheses, hydroxide. So aluminum 3 hydroxide. Okay, so we're reacting the acid and base. It's got a leading hydrogen, has a hydroxide in it. Okay. What do I suspect is going to be the products of reaction, or what is a product of neutralization? Hydrogen and the OHs. Now, even right here, we have our first hint on the balance, don't we? I've got 3 hydroxide ions that I need hydrogens for. I need 1 hydrogen for every one of those. You see that? So I'm going to form, first of all, water, H2O. And H2O was formed by a hydrogen plus a hydroxide ion. I've got 3 hydroxides, so I need to pull 3 hydrogens to form 3 waters. My 3 hydroxides will be in this molecule. I'm going to need 3 of these to give me the hydrogens that I need to balance that to form that. Okay? Another way to think of it. I've got 3 partial waters. I need the other piece to make water, and when I get all those pieces, I will have 3 waters. And then in addition to that, we're going to have a salt. And what is the salt going to be made of? Well, we've already accounted for the hydroxides. We've already accounted for the hydrogens. What must my salt be? It's going to be the metal from my base and okay. What is the charge of the polyatomic?
Is it just like that?
Pardon?
Or is it just a 0.5? Or G?
Let's go back. Not a lot of confidence in the room. Where are we spinning back to? I think it's module 5. It's just a -1, isn't it? Should be beginning of 5. Right, nitrate is a -1, as is nitrite. They're both -1s. So, what is hydroxide? What was its charge? -1. That's why we knew it was aluminum 3 hydroxide. And we're forming a molecule that has an NO3. It's got a different second half, but what is that charge? It's the same as this one, right? So how many of them do we need?
This one.
This has a charge. This polyatomic ion has a -1 charge. This has a 3 positive charge. So we need 3 of them. We need 3 at -1 to balance out the 1 at +3. Look at inside the parentheses. We have a polyatomic ion that has a charge of -1. Look at its original form. We have a polyatomic ion with a charge of -1. OH and NO3 are functionally interchangeable when we're building up the salt. NO3, nitrate, has a charge of -1, as does OH. We needed 3 of these, so we need 3 of these. We know that it's going to be some combination of aluminum and nitrate. So AlNO3 is our basic form. Now we need to check within the molecule, and does that make sense? Knowing that this is a -1 and this is a +3. No, it doesn't. We need 3 of them. Now we can go back and balance the equation, make sure that it's balanced. So try to ignore my slash marks here. And recognize that this is part of the product. I didn't have that in a good space. So reactants, products, we have hydrogens, nitrogens, oxygens, and aluminums. On the reactant side, 3 hydrogens for 6. Nitrogens, 3. Oxygens, 3 at 3 is 9, plus 3 is 12. And aluminums, we have 1. On the product side, hydrogens, we have 3 sets of 2, which is 6. Nitrogens, we have 3 sets of 1, which is 3. Oxygens, we have 3 sets of 1, which is 3, plus 3 sets of 3, which is 9, which forms 12. And aluminums, we have 1 of 1. It's balanced. So 3 HNO3 plus 1 AlOH3 neutralizes to produce 3 H2O and 1 AlNO3 sub 3. Apologize for the quality of the board, the marker, and my lack of spacing to put that on the second row. But in your notes, hopefully you wrote this across as one line. Generally quiet. What's the sense? Feeling confident, overwhelmed? Those are 2 different, right? Where are we on the confident to overwhelmed continuum?
I'm like right in between.
Right in the middle?
Yeah.
Okay. Well, how do we overcome that? It's by practice. And so you're at the place now where on your own 9-4 is in the text. I'll go ahead and work 9-4 on the board for the rest of the period. Got about 6 minutes, 7 minutes. You can work 9-4 on your own. The answers are in the book, but I'll work them up here so you can see them as well. And you'll be dismissed at the bell. Okay? Thank you.